Okay, so let's dive into this. We've got a real cosmic head-scratcher today, haven't we?
We really do. It involves a galaxy quite far away, NGC 10068. Some people call it the Squid Galaxy.
The Squid Galaxy, right. And it seems to be sending us some mixed signals, you could say.
That's a good way to put it. Our big detector down in Antarctica, IceCube, it's seeing a strong, steady stream of neutrinos coming from that direction.
Okay, neutrinos, those tiny, almost ghost-like particles we've talked about before.
Exactly. But the weird part is we're not seeing the amount of high-energy light, the gamma rays, that we'd normally expect to come along with that many neutrinos.
Right. Usually they're kind of a pair, aren't they? Big neutrino signal, big gamma ray signal from the same energetic event.
Typically, yes.
Yeah.
Especially when you have things like protons smashing into photons at high speeds. That tends to produce both. So yeah, seeing lots of neutrinos from NGC 1068, but only a faint gamma ray glow is...
Well, it's puzzling. It's like hearing thunder without seeing the lightning strike. Very strange. And you, our listener, pointed us towards some really interesting new research trying to figure this out.
That's right, some fresh ideas on the table.
So that's our mission for this deep dive. Figure out what this new explanation is for the Squid Galaxy's neutrinos and, why it actually matters.
Sounds good. Maybe we should start with a quick reminder about neutrinos themselves, just how elusive they are.
Good idea. They're fundamental particles, super, super tiny.
Incredibly tiny, and they hardly interact with anything. They can zip through planets, stars, even light years of lead, like nothing's there.
Which makes them incredibly hard to spot.
Exactly. That's the challenge.
And that brings us to IceCube, doesn't it? This isn't your average telescope looking up at the sky. Can you remind us how this thing works buried down there in the Antarctic ice?
Sure. IceCube is unique. It's basically a huge block of ice, a cubic kilometer, deep under the South Pole, filled with over 5,000 extremely sensitive light detectors.
5,000? Wow.
Yeah. And the idea is, very, very rarely, a neutrino flying through will actually hit an atom in the ice.
A direct hit.
A direct hit. It produces other particles that then give off a tiny flash of blue light, Cherenkov radiation.
Yeah.
And it's that faint flash that the sensors pick up.
So you're seeing the very faint evidence of this incredibly rare interaction.
Precisely. It lets us trace the neutrino's path back, figure out where it came from.
It's amazing technology. And I remember seeing a quote from Alexander Kusenko in the notes saying we really need these neutrino telescopes alongside our regular light-based ones.
Absolutely. Because light, even gamma rays, can get blocked or scattered by dust and gas out there in space.
Right, cosmic fog.
Pretty much. But neutrinos, they punch right through. They give us a direct line of sight to the most powerful events in the universe, stuff we might otherwise miss completely.
Okay, so back to the Squid Galaxy, NGC 1068. IceCube sees lots of these high-energy neutrinos coming from it.
A significant number, yes. A high flux. But the gamma rays detected from the same direction are much, much weaker than our standard models predict for that many neutrinos.
That's the core anomaly. The gamma ray signal is just too quiet.
Exactly. Way quieter than you'd expect if, say, protons were smashing into photons in the area around the galaxy's central supermassive black hole.
So the usual explanations, they kind of fall short here.
They have limitations, yeah. They struggle to explain the specific ratio of strong neutrinos to weak gamma rays. And that's what pushed scientists to look for, well, a different kind of source.
Which brings us to this new idea, and it involves helium. That sounds a bit out of left field.
It is a different approach than focusing just on hydrogen, which is, the most common element. This new theory comes from researchers at UCLA, Osaka University, and the University of Tokyo's Kavli Institute.
Okay.
And their proposal is that these neutrinos aren't primarily coming from hydrogen interactions, but from helium nuclei getting ripped apart in the galaxy's jets.
Helium nuclei getting ripped apart. Okay, walk us through that. How does breaking up helium lead to neutrinos, but not a lot of gamma rays? My high school physics is a bit rusty.
Fair enough. So the idea centers on the incredibly intense ultraviolet light UV radiation that's pouring out from the region very close to NGC 1068's supermassive black hole.
Right, the very energetic core of the galaxy.
Exactly. Now imagine you have helium nuclei, which are made of 2 protons and 2 neutrons, caught up in the galaxy's powerful jets, getting accelerated to near light speed.
Okay, super fast helium.
As these fast helium nuclei fly through that intense UV light field, they collide with the UV photons.
Like a cosmic collision course.
A very energetic one. These collisions are powerful enough to actually break the helium nucleus apart. It fragments.
Into its bits. the protons and neutrons.
That's right. 2 protons, 2 neutrons suddenly flying free.
And this is where it gets different from hydrogen, right? What happens next?
This is the key part. The protons, being charged particles, will interact with magnetic fields and so on. But the neutrons,
Yeah?
well, free neutrons aren't stable.
They decay.
They decay fairly quickly.
Yeah.
And, crucially, when a neutron decays, one of the things it produces is an antineutrino. But, and this is the important bit, this decay process itself doesn't directly create a lot of gamma rays.
Ah, I think I see it. So if you had hydrogen, which is just a proton, interacting with photons, you'd likely get a reaction chain that makes both neutrinos and the bright gamma rays we expect.
Generally, yes. Proton interactions often lead to particles called pions, which then decay into both gamma rays and neutrinos. It's hard to get one without the other in large amounts.
But with helium, you break it open, get these neutrons, and they decay, making neutrinos without all the gamma ray fireworks.
Exactly. The neutrons provide what Koichiro Yasuda, the lead author on this study, calls a gamma ray silent pathway for neutrino production.
Gamma ray silent. That makes sense. It bypasses the usual noisy process.
Precisely. It offers a way to generate a strong neutrino signal without necessarily generating an equally strong gamma ray signal.
Okay, but hang on. We do see some gamma rays from NGC 1068, right? Just not as many as expected. How does this helium idea account for those?
Good question. The theory doesn't say 0 gamma rays are produced. It suggests the gamma rays we do see are likely coming from secondary processes. For example, when the helium breaks apart, or in subsequent decays, electrons and positrons can also be produced.
Okay.
These electrons and positrons, as they zip through the magnetic fields and radiation near the black hole, can produce gamma rays through processes like inverse Compton scattering. But the amount they produce is consistent with the lower, weaker gamma ray signal that's actually been observed.
Got it. So the main neutrino production is quiet, gamma ray-wise, but there are other side processes that create the fainter gamma glow we detect.
That's the picture, yes. It allows the model to match both the strong neutrino flux and the specific energy signatures of both the neutrinos and the dimmer gamma rays much better than previous models could.
It sounds, well, elegant, actually. It seems to tie things together nicely.
It does seem to offer a more coherent explanation for this specific observation from NGC 1068.
Okay, so solving this puzzle for one galaxy is cool in itself. But what does this mean for the bigger picture? What are the broader implications if this helium idea turns out to be right?
Well, for one thing, it significantly changes how we think about cosmic jets from active galaxies. It suggests they can be powerful neutrino sources even if they don't shine brightly in gamma rays.
Which means there could be other galaxies out there like this, pumping out neutrinos that we haven't noticed because we were mainly looking for the gamma ray signal.
Exactly. It opens up the possibility of a whole population of hidden astrophysical neutrino sources, galaxies that are bright in neutrinos but faint in gamma rays, which might have slipped under our radar until now.
Wow, that's a pretty big implication, hidden neutrino factories across the universe.
It is, and it also tells us a lot more about the crazy environment right next to supermassive black holes.
How so?
Well, the theory depends on that intense UV radiation field near the black hole being strong enough to break apart helium nuclei. So if the theory holds, it gives us a way to probe the conditions, the radiation intensity, particle acceleration, in that extreme region, which is otherwise incredibly difficult to observe directly.
So we're using neutrinos as messengers from the black hole's doorstep, essentially.
In a way, yes. Alexander Kusenko made this point too. It helps us learn about that immediate environment. And remember, our own Milky Way has a supermassive black hole at its center. Understanding these processes in NGC 1068 could even shed light on what's happening, perhaps more quietly, at the heart of our own galaxy.
That really brings it home. Learning about a distant galaxy helps us understand our own cosmic neighborhood.
It absolutely can. These fundamental processes are likely universal, and thinking even broader, this kind of fundamental research often has unexpected payoffs down the road.
You mean the whole basic science leads to unforeseen technology thing?
Exactly that. Kusenko uses the example of J.J. Thomson discovering the electron. At the time, it seemed like a purely academic curiosity.
Just figuring out what cathode rays were made of.
Right. But that discovery was the foundation for all of modern electronics. Without understanding the electron, we wouldn't have computers, phones, any of this stuff.
And he mentioned the World Wide Web coming out of particle physics labs needing to share data.
And MRI machines coming from studies of nuclear magnetic resonance, something that seemed totally obscure initially.
It's a good reminder that you often don't know where fundamental discoveries will lead.
Definitely. And neutrino astronomy, as Kusenko points out, is still a relatively new window on the universe. We're still figuring things out. solving puzzles like this one from NGC 1068.
And that requires long-term investment, doesn't it? The kind usually supported by governments and universities.
It does. This kind of research doesn't always have immediate applications. It needs sustained funding, like the support this work received from the Department of Energy, Japan's WPI initiative, and the JSPS. It's about building knowledge, exploring the unknown.
The paper itself was published in Physical Review Letters just recently, right? April 18th, 2025.
That's the one. Yasuda et al. Neutrinos and gamma rays from beta decays in an active galactic nucleus NGC 1068 jet.
Okay, so let's try and wrap this up. This deep dive into the Squid Galaxy's weird signals reveals this really compelling new possibility. Maybe it's helium atoms getting torn apart by UV light near the black hole that's making all those neutrinos without the expected gamma ray noise.
It's a fascinating potential solution that challenges our older models of how these cosmic engines work. It suggests a quieter, neutron decay-driven path for neutrino production.
And it really highlights how science progresses, right? You see something unexpected, the standard models don't quite fit, so you look for new explanations, potentially uncovering whole new classes of objects or phenomena.
Precisely. It's about following the data, even when it leads you in surprising directions, and maybe uncovering these hidden neutrino sources.
It leaves you thinking, doesn't it? About how these deep dives into fundamental physics, exploring distant galaxies and tiny particles, might be laying the groundwork for future technologies we can't even conceive of today. What other cosmic mysteries, currently just puzzles for astrophysicists, might hold the keys to some future revolution?
That's the exciting and often unpredictable part of fundamental science. You never quite know what you'll find or what it might lead to.